Hello, everyone. Thanks, Victor and Alberto, for the invitation to this new edition of the summer school. I will talk for how long? An hour I have, right?
Yes,
Victor?
1 hour.
Okay. So I'll talk for about an hour on the research that we are doing here at IRI on event vision for robotics. And this is work that is joined with my colleague, John Sola, and also our PhD students, William and Yi. Maybe some of you already know what an event camera is. So I will just skim briefly through this type of sensor, which has appeared well over a decade ago. And it's brings possibilities to do things with computer vision that previously were not possible, given different properties that it has. And basically what it does, it gives you the changes in intensity at every single pixel, but each pixel at a time. It doesn't give you entire images, it just gives you the pixels that change intensity. So they fire logarithmically with the change in brightness, and you get in the USB bus of the sensor, you get this asynchronous stream of data, which gives you only the coordinates of the pixel that changes and also the timestamp. If you compare this is an old image from the group of Scaramuza, TTH. If you compare a standard camera with what you get from an event camera, is that in a standard camera, you get frames one at a time, the entire frame. In an event camera, you get the burst of events at a much higher frequency. But when there is no motion, you don't get events, of course. And one thing is that even when in a conventional camera, there's motion blur, in the case of event cameras, you don't have that. So this is nice because you have not only disregard the problem of motion blur, but you also have non-redundant data on the stream, so you have much lower bandwidth. These are some of the advantages. For instance, since it has a high dynamics range, it reduces the effect of overexposure, and you can work with low contrast and low lighting. Event cameras have, in robotics, have been proposed to be used in tasks that in which conventional cameras do not work. So for instance, for scenarios with ultra-fast motion dynamics. So this is our objective, to try to see whether we can use these cameras for motion estimation in these very fast dynamic scenarios. So what I will present today are 5 different works in our group, 3 of them related with the use of cameras to compute motion estimation when you have features in the scene that you can extract, in our case, lines, because cameras are very good. These event cameras are very good at detecting the contrast in images. So they are very good at detecting edges in the image. For that case, we use lines. And there are 2 other works related with the use of neural networks for the computation of optical flow and also, in the end, egomotion. So first, high-speed event camera tracking. This is a work that our student William did during his PhD studies. It was presented on BMBC a few years ago. And our idea was to track the state of the camera, its position and orientation, but in scenarios, very fast motion. So the assumption is that we know the scenario. We have a scene made up of lines. And then in an event camera, what you get is the events. And in these images, you see aggregated event counts at conventional camera rate. But remember that you get the events at a much faster pace, at the order of microseconds. And those events that change from white to black will have positive polarity. The ones that change from black to white will have negative polarity. So this is the kind of data that you will get in an event camera. So in our algorithm, this is a conventional tracking algorithm, Kalman filter algorithm, in which you get an asynchronous stream of events, and then you have to do some steps in order to do the pose estimation. So first of all, is camera and distortion, of course, because you have the camera calibrated. You have to use the camera calibration parameters to undistort the location of the pixel in the image. And then select a set of events to build up, aggregate those events to build up lines, and then match those lines. So match each of the lines with the lines that you already have in your map, right? First, to distort the events, we used an exact formula for inverse radial distortion that has been published before. And then we get the events in windows of 100 milliseconds. And these are the type of events that you will get positive and negative events in windows of 100 milliseconds. And then you need a few heuristics to aggregate the events into lines. For instance, those events that are located in the corners of the lines are not good, and those events that are quite far away from what you expect that is a line are also outliers that you wouldn't like to accept. And then once you pass these two heuristics, then you can use some measurement models to match events to lines. And in the end, what you have is the distance from the event to the line that you have in your map. And with these distances, these innovation terms, so distance measurements are the ones that you use in your kernel filter to do the updates of the estimation of the pose. And basically, we have two different projection models. One, if you consider the camera to be your center of the one that you estimate, or the reference frame. And the other one is if you consider a fixed world coordinate frame and a camera moving. So with these two different models, you have a bit of change in the equations for the projection models. And then you have three different motion models. We use either constant position, constant velocity, or constant acceleration. And we compare our algorithms in using the three different models to see which one is best for our application. Just remind you that all the estimation of the rotations in our work is using Lie algebra. So this is straightforward, and perhaps you already attended or going to attend, I don't know, the order of the presentations in the summer school, Joan Solà, who talks on this Lie theory for estimation. So just to show you a bit of results on our filtering. When we have constant position model and we move at more or less low speed, as you can see, we can estimate the position orientation of the camera, and we compare the ground truth with an OptiTrack system in our laboratory. And you can also see that if you would try to do this motion estimation using conventional computer vision, it would just definitely would not work, because images will get blurred and it will be very difficult. But with event camera, we are able to do this quite fast. So as you can see, for instance, in this case, we have constant acceleration and a medium speed motion. We can estimate motions of about 1 meter per second and orientation speeds of about 5 radians. And then if you have very fast motion with the model of constant velocity and very fast rotations, our algorithm is able to obtain these estimates, even with angular speeds as fast as 14 radians per second. This is the most that we can achieve with our hand, moving the camera with our hand. But we decided that this might not be enough. Sorry, this was the largest. Strong handshaking, about 7 hertz, and even to see what the turning the lights on and off with the camera because of its properties, will be able to also estimate the motion properly. And this is the fastest that you can do, shaking the camera with your hand. And you can see that the tracker works relatively well. But then what we wanted to do is that we wanted to estimate the limits. We wanted to see what the limits of the tracker were. So we built this system in order to rotate the camera faster than we can do it with our hands. And this is a demonstration in which we have, in this case, an experimental validation in which the tracker moves at the order of 100 revolutions per minute. And this video that I'm showing here is reduced at 1/10 of the actual speed, right? So this is the fastest that our system would be able to perform the tracking at 950 revolutions per minute, and accelerations up well above 25 G. So I don't know about any other system that can do such fast motion estimation with an event camera. Now, the second thing that I want to talk about is, okay, this is estimating the motion of the camera, only taking into account the events not only using images, because these cameras also provide images and also provide IMU data, initial measurement unit data. But this one, the first one that I showed you, is only using the events and matching the events with the lines of a predefined map that you already know. Now, we want to do a similar thing, but also fusing with IMU data. In this case, we also use this non-scenario, and we have different ways of doing it. We can do, for instance, constant velocity or acceleration prediction at 10 kilohertz and IMU updates at 1 kilohertz. And so in this case, our goal is to compute, again, the motion of the camera. And there are two different strategies that we use. One strategy is using the events and fusing with IMU data. So we aggregate in this strategy, which is our slowest strategy. You use the events and you fuse the events in windows of 300 milliseconds, and then use the input from the IMU, which comes at 1 millisecond rate. So you get in your filter estimates at 300 microseconds. So these estimates at 300 microseconds, you get updates from the windows of events and also from the IMU, and predictions with a constant velocity model or constant acceleration model. So this is a scheme of the strategy, but this is just straightforward Kalman filtering again, a lot of the different heuristics that you do to do the tracking. This is the same event line data association that we did in the previous work, so we use the same system here, right? And also, as I mentioned, we use Lie algebra for the formulation of the rotations in the prediction and the updates. So we have two different ways of using the event corrections. One of them is using instantaneous model, that is, sorry, of using the IMU corrections. One is using instantaneous model, which is just using the IMU readings as they come. And another one is using the IMU readings, computing average of the IMU readings and updating with these averages of the IMU readings, right? These two that I just mentioned. Then we have a different strategy, which is doing predictions with IMU and then doing the updates with events. So in this case, we have a much slower window, which is 1 millisecond. So you get the events at 1 microsecond and you aggregate events in windows of 1 millisecond. And then you have also the updates at 1 millisecond, and you have this frame rate of 1 millisecond for the fusion of the events and the IMU readings at the same time. So the strategy is similar to this one. And again, the motion models that we use are for the event plus IMU, constant acceleration plus instantaneous acceleration model, and constant velocity plus mean acceleration model. Of course, in our models, we also have to estimate the biases of the IMU. These are states that are also included in the estimation. Then for the IMU plus events, this is the state transition model, which is standard as well. And we do this at central window times center at the IMU timestamp. So the sensor fusion, the measurement models are straightforward as well. These are instantaneous acceleration model, which is just the linear acceleration and angular velocity. And then we have the mean acceleration model, which uses mean values of two different readings of the accelerations and also two different readings of the constant velocities. So as you can see, both of these models take into account parameters for the angular velocity noise and the linear acceleration noise, which are given by the characteristics of the camera in this data sheet specifications of the camera. Then there's one little thing that we needed to do for this to work is that we needed to adjust. This is an engineering trick that we needed to do. We needed to adjust the drivers that are available for working with these devices. For instance, the Davis Ross driver. We need to do a modification in order to be able to publish the messages at the rates that we needed with all the data from the events and the IMU. So I'll give you just some experiments on this. In this case, we're shaking the camera at about 6 Hertz, changing position orientation. And in the little boxes that I show there in the plots, we will zoom in on those plots and this is a zoom in, and in here you can see the different tracking. In this is the ground truth data, right? So the red and blue lines or black lines, this is ground truth of the different values. And then this is the estimate of the different methods. And here you can see constant velocity plus mean acceleration, or simply constant velocity, or constant acceleration plus independent accelerations, or constant acceleration, and also the other method, which is IMU plus events. And all of them, they perform similarly. Some little advantages. The IMU plus events, which is the one that works at the lowest rate, is the one that gets the least error, but it's also the one that provides updates at a lower frequency. And if we compare the results for different scenarios, we have like a cube, unclaimed, and then 3-heteron. We have different scenarios that we implemented. And we compare all the methods. We can see that the constant velocity model and the IMU plus events are the ones that perform the best. In here again, you can see this is the computational burden of using this constant velocity plus the mean acceleration, or constant velocity, or constant acceleration plus independent acceleration. This is the computational burden that these methods add to the system, but still they allow us to do real-time estimation. You can see here that this is a factor of real-time performance. We are well above the 1, which is the real-time performance requirement. Again, we wanted to test our system to the most extreme motion case, and for this we had to develop a new 4-bar mechanism. The one that we used for the other previous experiments was not sufficient for this new test, because we needed to change the speed differently. So we developed a new mechanism, which is this one. In this case, you can see now the camera moving. In the other case, it was the pattern moving and the camera stationary. In this case, it is the camera which is moving, and the pattern is what is stationary. And we needed to do this change because, of course, we need to move the camera to experiment the IMU readings. So as you can see here, the tracker fails at frequencies of about 12 hertz or 14 hertz. The different methods fail at different frequencies, right? So the IMU plus E stopped working earlier. The constant acceleration method stopped a little bit further, then the constant velocity plus mean accelerations, and finally the one that uses only constant velocity. I will zoom in into these little plots, and you can see here also the ground truth compared with the data of the different methods is plotted in these plots. One thing that is important to point out is that there is one point in which the IMU saturates when the acceleration are faster than what the sensor can read, the IMU sensor can read, then the estimates are not good anymore. So you can see in gray, we have blurred here the regions in which the IMU saturates. So at frequencies of about 12 hertz, then in the case of the X direction, and even at the rates about 8 hertz, in the case of the Y direction, the IMU saturates, and so the estimates are no longer valid. This is what you can see here, right? This is because of the maximum capacity of the IMU sensor that is included in this Davis camera. Of course, there might be other IMU sensors more expensive that have better performance characteristics, but this is the one that we have used. Now, this was for camera tracking using events, and camera tracking using events and fusing with IMU. Now, whether we thought that could we use this to do a full SLAM system? So we implemented a SLAM system in which the tracking part is implemented with these methods, and the mapping part is a module at a lower frequency of a PTAM system, a parallel tracking and mapping system. Right, so you can see here, this is the tracking that I have explained already, and then this is the mapping thread. So in the mapping thread, there are a lot of heuristics in which we have to do ray tracing to aggregate events into lines, and then from this ray tracing into voxels in which we have boats of events that correspond to lines. Then we have to do some line extraction, and then line fusion and line aggregation in order to eventually build those lines. And then since we have in the mapping thread and in the tracking thread different estimation mechanisms for the pose of the camera, then we have a bundle adjustment module that fuses the two together to compute the final estimate. So to do 3D reconstruction via ray tracing, this is a simple technique that has a voxel representation represented in inverse depth, in which you project the events into this voxel representation and you do just boat counting. And eventually, if you do this from different viewpoints and you have to keep your different estimates of the location of the camera to do this, project all this to your reference keyframe and have this voxel representation at your reference keyframe. And with all these boatings, you end up having images like this one, right? So this is one of the slices of the voxel representation, and this gives you the largest voting of the locations in which there should be lines. And in the end, you have to concatenate this in order to get the location of a line, right? So to do this line recovery, what you have to do is to get those locations in the voxel representation in which you have this maximum set of boats, and then do some heuristics. In this case, for instance, you have to estimate depth. You have to do this masking of the events of the boats, and then do some Hoff transformation to do filtering to remove the outliers, and then do this Hoff transformation to get the lines. And at the end, you need to do some line merging in order to estimate which are the lines that you will include in your map. Once you have sufficient length of a line and sufficient number of boats, that you can say, okay, I can include this new line in my map representation. So this is some more of the same stuff, but I will not go over this. And then you have this bundle adjustment in order to compute the estimate of the position of the camera. Basically, how you have is you have your Kalman filter that is estimating the location of the keyframes, and then you have a new window with different keyframes, and you have to do some overlapping of these windows to do the optimization. So you maintain this. And this is a straightforward bundle adjustment for this optimization of the lines and the position of the camera at the same time. And then one other thing that is important here is you need to do some initialization of the location of the camera. And since you don't know anything about the map at the beginning, then what you can do is do some Hoff transform on the images to get the original lines. And then with these original lines, you set your original keyframe, and from this keyframe, you continue working with the estimation, right? So there are now some experiments about this. This is, for instance, mapping on a large sequence. You have this, again, regular motion, and as you can see, the algorithm at the lower frequency, the mapping part is including the new lines in the map. And the much higher frequency, you still have the camera motion tracker that we developed before with the IMU. Then we have compared the results of this mapping mechanism with SVO, which is another technique for visual odometry with events, and also with ORB3, which is for conventional computer vision. So this is the results of EVO. This is SVO in green, and then ORB3 in blue, and you have all of them. At one point, the SVO fails, and the other systems continue working. And this is when you have challenging lighting conditions, because then SVO doesn't work with these challenging lighting conditions. And this is another evaluated sequence. In this case, this is a trihedron. And the same, you can do your mapping, including this aggregating all these lines into your map. And with challenging lighting conditions, there are some systems that we cannot compare to, but in comparing with EVO, we have comparing with the ground truth that you have with the OptiTrack, our algorithm, the model in which we use constant velocity for predictions, performs a bit better than EVO. And when you do not have this challenge in lighting conditions or fast motion with regular motion, then our method exceeds some of the state of the art, but there are some scenarios in which ORG3 and SVO outperform our technique or are comparable to ours. Then there's another evaluation, which is IMU plus the E variant and the mapping. And this is this case. And again, we do the mapping. And as you can see, the mean position error is similar. In this case, the IMU plus events is the one that performs with least error from all the different methods. But again, this is a mapping technique that has an output of the position of the camera at a lower rate than the other one that uses only events and IMU and not with the other fusion technique for the IMU. Also, we needed to, there are some parameters that are in the system that need to be analyzed. One of these is the event window size that we use versus the error, right? So in this case, for event window sizes of 1 millisecond is in the cases in which we have the least Z-score. So this is the best estimation. And if you use larger event window sizes, then you have larger standard deviation for the Z-score. And if you get also events with smaller size, much faster events with smaller size, you also do not have sufficient events to aggregate into lines, and then also the error increase. The same regarding the number of lines that you use in estimation during the map estimation. So when you use numbers 12, 14, 16 lines, then your estimate is okay. But if your map has less number of lines in the scenario, then you don't have sufficient information also to estimate properly the position of the camera. So the error increases. Okay, so far this is, I have eaten already half hour, so it's okay. So far this was for using event cameras, using conventional computer vision techniques to do very fast estimation of motion of the camera, and also one technique for doing mapping or doing SLAM. But in this case, you need features in the scenarios. That is, you need lines, and doing this without features is a little bit more complicated. So we have started to investigate what can we do using learning to do also motion estimation for the camera. So our first approach into this was try to understand what can be done with a spiking neural network. With a spiking neural network that is used to compute optical flow. So spiking neural networks are interesting because these are neural networks that are asynchronous in that they can, because of the synchronous data of the event cameras, they are actually quite well tailored to treating the data from the event cameras. Contrary to conventional neural networks, you only get firing at one neuron at a time and then propagate the data from that neuron further on in the network before needing to do convolution with the entire image or the entire size of the layer. But the bad thing about this is that it is not straightforward to do backpropagation. There are new techniques now in which they have what they call circuit gradient to do backpropagation. But at the time when we started this work, there wasn't good ways to do backpropagation. So we used self-learning in the method that we implemented with the spiking neural network. And our objective was to compute the echo motion of the camera using a pre-trained spiking neural network that was used to compute optical flow. And in this work, what we do is we use this pre-trained network and then propose a robust optimization algorithm to optimize the constraints of the normal flow elements in order to compute robust aggregates of normal flow before computing the optical flow. So what is this? What is a neural model in a spiking neural network? The model that we use, and one of the most common in the literature, is this leaky integrate and fire model, in which in the neuron you integrate data from the previous neuron or the input layer from the events of the camera, and once you get sufficient number of firings or sufficient number of events in that little pixel, then the neuron fires. And then it has a refractory period in which the neuron doesn't do anything, and then you continue. And it has different parameters, such as the homeostasis or the presynaptic trace, etc. The learning rule is STDP, spiking time-dependent learning rule. And this spiking time-dependent learning rule, basically what it does, it adjusts the weights in the neuron with this time-dependent plasticity that occurs on the neuron. So this is the STDP learning rule. I will not go much into this. What I will do is that I'll explain a little bit what we did. So you have these data sets, different data sets. One that is made with a DBS simulator, and another one that is made using an optical flow on a rotating disk. So you get events from these two different data sets. And then our architecture of network architecture is as follows. You have the input data, which comes from the camera, and the input layer. You have two layers because you have the positive and negative polarities of the events. And then you have a convolution layer and a merging layer, and then another convolution layer, and then pooling, and then from this pooling layer, then you compute the dense optical flow or the dense ego motion estimation after that. These are parameters of the layer. The important thing is that the kernels that you learn in this convolution layer, the ones that you see here on the left and also on the bottom part of the chart, they represent primitives for velocity direction of motion. So for instance, if you have a diagonal edge that is moving from top left bottom to top right, you will get something like the one that you see on the first kernel in the larger part of the bottom of the image. The first one in the bottom of the image of the larger kernels is one that represents this type of motion. So in the end, each of these kernels represents the ones that you are learning with this self-learning technique, represents velocity directions of motion in the image plane, right? And the thing is that you train a network with a data set, and then once you have trained these kernels, you use these kernels to compute motion on a real sequence. And if the motion is similar in speed and directions of motion to the one that you use during training, then you will be able to compute optical flow quite decently, right? So I'm going to show you. I'm going to show you results of this. So I'm going to go. Okay. So once you, there's one step further. You have these kernels that represent directions of motion in the image plane. So from these kernels, you have to actually compute the optical flow and in that location. So how do we go about computing this optical flow? Basically, what you get is you have to use the histograms of these kernels and then do optimization on the histograms of these kernels. And this is what you do. You compute, as you can see in the left part of this picture, what is the optical flow vector that is estimated by taking these two different kernels and doing the matching of these two kernels, right? One thing is that when you do training, you might not have a uniform distribution of kernels in all different directions and speeds, and this is because of the training data that you use. So the training data has to be sufficiently rich to represent all different directions of motion. And in the ones that we use, you can see which is the kernel distribution. So in terms of orientation and speed, right? And there is so many kernels that you can use to represent your data at the end, your training. So in this case, for instance, we use 64 kernels. So it is as all the different speeds of direction, direction of motion and speed are just quantized into the 64 different vectors. So this might not be sufficient to compute a good estimate of the optical flow, right? Now, there's also one point in which you have, let me show you here. Imagine you are in the middle layer, which is merge and convolution, and then you have to do the pooling. So to compute the pooling, you have to get the average of the directions of motion from the previous layer into the new layer. And in computing this average, you have to merge different normal flow estimates into one flow estimate. So this aggregation or merging of different flow estimates into one larger flow estimate for that window, or that smaller window, cannot be done naively. There are techniques in the literature in which they do it either intersection of constraints just by averaging, or by just computing the intersection of two different lines. And we have seen that these might present problems when you have noise data. So we presented a new technique in which you robust estimation of constraints, intersection of constraints using some least squares optimization, and also using Ransack to remove the outliers. So this is presented in that paper, in which we have the intersection of constraints as the eigenvalue of the eigenvector that optimizes this function. Now, from this flow estimates, normal flow estimates, you have to compute the ego motion of the camera. And the ego motion of the camera, you need to compute the rotation part and the translation part. So for pure rotation motion, the computation is straightforward, and for pure translation motion, also the computation is straightforward, albeit scale. So since in this training data you do not have the scale, you don't have the depth, and you don't have the scale, so the only thing that you can do is compute the direction of motion, but not the speed of translational motion. So this is one thing which is a limitation of this type of system, right? So here are some results of this angular velocity estimation, where, as you can see, in the first row you have the events as they come in the input data, and these are, well, positive and negative events, and then you have the normal flow, which is the color encodes the orientation, and the length of the vector encodes the speed of the direction. And then from this, you aggregate this into an optical flow vector. And in here you have in green, which are the inliers of the robust optimization, and in red, the outliers. And in gray, you have the ground truth. And using these inliers, then you can compute with the previous equation that I showed you, you can compute the angular velocity estimates. And you have the angular velocity for all the three different terms of orientation. So you see that you can different situations in the image, you can compute the velocity of the camera. And you have here the time scale, which is in the millisecond range. So this is for a very short period of time of 100 milliseconds. The thing is that in the end, what you have is the spiking neural network can produce output rate of estimates of motion at a very fast pace, and much larger than you will get with a conventional neural network. But the thing is that you so far can estimate rotation at the scale at which you have trained the data, at the time scale at which you have trained the data. So we investigated whether we can reduce this time scale and also compute the rotational angular velocity using these scaled time scales. And these are results in which, well, you can do this as well. And this is a small video. I think there's a small video here. This is an example of a window of 100 milliseconds. It is very much slowed, in which you also, in this one you have translational motion. This is translational motion at constant velocity in diagonal. So you have positive and negative events that occur in this windmill pattern. And as you can see in the second box in the window, you have first the events, the positive and negative. In the second part of the window, you have the neurons that are firing in the merge layer for the optical flow. And then you have the aggregated flow vectors, the normal flow vectors in the third window, the larger ones that you see here. And then in the end, you have these computed velocity vectors, translation velocity vectors. Since you are moving diagonally, then you have the X and Y, which is the green and the red estimates of the motion, and the Z value is 0. So the network is able to estimate correctly the direction of motion. But again, this is the whole sequence is for 100 milliseconds, which is reduced considerably in time. But this is only for translation and without scale. So you can compute rotation velocities, you can compute translation without scale, but you cannot compute robustly, you cannot compute both yet using this type of systems, this type of spiking neural networks. Right. Now, so this is our first attempt at trying to use a spiking neural network for that. And then we switched a bit our focus and we tried with a different type of network, which is called an event transformer. And what we developed is a hybrid recursive neural network with a visual transformer. And our objective was not to go all the way to compute rotation and translation estimates, that is ecomotion, but just to compute the optical flow. So there are other works that compute optical flow using conventional networks, and what we propose is to use a visual transformer. In the past, there has not been used visual transformers for this topic, so we were one of the first in doing that. And our argument was that the visual transformer was interesting to use in this particular problem because the transformers in general, what they do is they encode long-range dependencies in the data. And we argue that we have long-range dependencies in the image plane when you are doing rigid body motion. That is, the motion of the elements in the scene are correlated not just locally around 1 pixel, but globally in the entire image. So we wanted to encode these long-term relationships in the image using these visual transformers. So we do end-to-end training using self-supervised learning. In this case, they're using contrast maximization loss. The architecture for the network is a U-shaped network, conventional RNN U-shaped network, like this one, with encoder and decoder like this. And also what we did is that we included this transformer block in the middle. And this transformer block has the visual encoders and decoders, and this is the architecture for the visual encoders and decoders that we used. These are some details on the parameters of our network that I can, well, they are in the paper, and also I can share if you need. And the type of learning that we did was supervised learning with contrast maximization loss. And the contrast maximization loss, what it does, it compensates the motion, the blurring the image of events, just warping events at the different timestamps. So what we do is that we generate per pixel and per polarity average timestamps for each of the events, and we compute what is called the image of warped events. And the maximization loss is simply the scale sum of these square temporal images that we build. And in our loss equation, we also include a regularizer, a smoothing regularizer at the neighboring pixels. So in our network, we did some ablation studies in which what we do is we use different numbers of transformer blocks and the residual blocks in the network. So we ended up deciding that the best performing system was the one in which we had 4 transformer blocks, as you can see here in the plot. I mean, in the table. these are some, this video works, yes, this is some results of our method compared also, this is the ground truth flow from the data sets that we use. And this is two different networks that are already in the literature. One is called COM-GRU plus EV-flow, and another one is called FireNet. And this is our network that uses the event transformer. And then we have here some of the results. The methods that are shown on black, with the titles in black, these are semi-supervised learning, and they are shown here only as a baseline of what is the state of the art in this. But these are not self-supervised; these are semi-self-supervised. The ones that are shown in the bottom, these are self-supervised, and these are the ones that we compare to, and the ones that are in blue. So our method performs well in some of the networks, like the outdoor day one network scenario, and also in the indoor flying scenario, but it's not the best performance for some of the indoor flying scenarios, as shown here, in which EV-FlowNet2 is performing best. This using the FPV dataset. But still, we are there with comparable or competitive results in some of the networks, in some of the data sets. And this is all I have. So I think I have used not all of my time, and I have at least 10 minutes if you have questions that I can address. So,
do we have any question?
by the way, I'm going to put the presentation again. If you are interested, there are a number of references that you can search if you are interested in this type of research. I'm just going to aggregate them, all of them, in this last slide. So this is for the tracker. While we here for the questions, I'm just going to add this at the end of the presentation. This one is for the fusion with the IMU. This one is for the mapping and tracking all together. And then we have the two CNN references. This one for the spiking neural network. And this one for the event transformer. No questions at all, not even in the chat. Let me see. No. So nice. Can one be taught its coding? What is your question again, Samuel? I do not understand your question. Okay, Jaiman, Josh. What is the difference between a spiking neural network and a classical one? In a spiking neural network, you get the input data. You get events one at a time in an asynchronous fashion. So you cannot treat, in a spiking neural network, you cannot treat all the data in a layer to do convolution like you do in a conventional network. The only thing you can do is move forward with your learning rule, like spiking time-dependent plasticity, the data from one layer to the next. But it is difficult to do backpropagation. So the main difference is that you cannot do backpropagation easily in a spiking network, spiking neural network. Although there are methods now that use hybrid networks, and you have few layers that are spiking, and then once you aggregate data, then you start doing things with a conventional network and so forth. Or there are some methods to do backpropagation with spiking neural networks using what is called surrogate gradient descent, for instance. But this is newer stuff that is appearing now. But the main issue is in a spiking neural network, you do not have the ability to do convolution in entire layer like you do with a conventional network. Coding in terms, Samuel, coding in terms of camera tracking. So what do you mean by that? The language that we use for doing this, the software coding, or what do you mean by coding? The programming of the system. Okay, everything is programmed in C++, and it uses ROS for data handling and visualization purposes. But basically the entire coding is in C++. And then there is this Lie algebra library from our group that we use, which is just a library, which is also called in C++. And you can, the references are in the paper. You can access this Lie algebra tool also to do the rotation estimation part. Which IMU are we using? We are using the one that is embedded in the Davis camera, which is, yes, this 1 kilohertz IMU that responds as fast as 9G, no more than that. So it's not that expensive IMU. It's the IMU that is already included in the Davis camera. And this is one nice thing about this is that the reference frames of the camera for some reason the system kicked me out. I'm back in. And as I was saying, is the IMU is the one that is in the camera. Let me go back to the messages. Do we have master's thesis open in our group? Yes, we have topics that we can work on. For instance, I'm interested in learning features for this tracking that don't have to do with the lines. So that's one thing that I want to do. So using using neural networks, learn the features that are optimal for doing it. Another one is to do integrate what we have done for the tracker into one of our drones. So that's another thing we want to do, to actually do the experiments with one of our drones, not just with our hand or with the mechanisms that we have, and do the connection between the tracking part and also the motion estimation part.